The following presentation is a focus on water vapor and CO2 and the effect each contribute to global atmospheric conditioning and global temperature control. Scientists and politicians have chosen to ignore that carbon dioxide in the atmosphere is necessary for life and that more is needed, not less. They have claimed that carbon dioxide is a pollutant and causes global warming, rather than acknowledging that water modulates the climate and together with carbon dioxide sustains life on Earth. The following video is not words and emotional pleading to reduce CO2 production and save the world. It is factual science information and is backed up by eons of historical weather. There is no doubt that oxygen is essential for human life, but water is just as important, not only for human life, but for a habitable Earth. Without water, Earth would be another planet devoid of life. Water vapor in the troposphere dominates the greenhouse effect and modulates the climate so life can exist. To begin this presentation, there will be several graphics that describe most of the information that scientists and engineers have documented about water on planet Earth. For centuries, humans have studied and conducted experiments to verify this information. Without the knowledge gained over the last 250 years, most of the improvements humans have made to living conditions on Earth would have been impossible. Earth's outer core is made up of approximately 71% water and 29% land. Humans inhabit approximately 0.5% of land, and roughly 12% of land is used for agriculture to sustain human life. This graphic shows the approximate percentages of global land mass and water. It is interesting that Africa and Asia make up nearly half of the world land mass, while the Americas are approximately 28%. European countries are only 6.9% of land, and Australia is 15.1%. Here is a graphic that shows the estimated distribution of Earth's water. Interestingly, only 96% of all water is saline water in the oceans. Humans rely on fresh water to survive. Fresh water makes up approximately 2.5% of all water on Earth, and it is not evenly distributed between the oceans and on land. Furthermore, about 98% of the fresh water is locked up in glaciers, ice caps, and groundwater, leaving only about 2% flowing through rivers, streams, and in lakes and reservoirs. This 2% is where mankind obtains water needed to sustain life. Because of nature, man has had to figure out how to utilize this 2% in the best manner. I will not get into the politics of water, but you all know that it has long been a contentious battle regarding water rights among peoples of the world. This graphic is a very simplified depiction of the water cycle on Earth. It is misleading because it focuses on fresh water and land that makes up a very small part of the water cycle. It shows the evaporation and condensation processes, but lacks information that is essential for understanding why the Earth's water cycle is so complex, and especially the profound effect it has on Earth. I hope the rest of this presentation will help to enlighten you on this subject. This graphic gives you an idea of the unbelievable amount of water on Earth. Anyone that says water is not the dominating factor in modulating temperatures of Earth's troposphere must have come here from a waterless planet. The troposphere of planet Earth contains a huge amount of water vapor that controls temperature and other phenomena to make Earth livable for humans. Carbon dioxide does not have the properties or the volumes necessary to be even a minor player in controlling temperature of the Earth's troposphere. This graphic shows more of the water cycle and begins to give an idea of the complexities involved. One can only imagine the many factors that must be taken into consideration to predict climate changes when the characteristics of the atmosphere are changing constantly at a variable rate all over the world. No computer has ever accurately predicted future changes in Earth temperature. Likewise, computers have not been able to hindcast Earth temperatures of the past. This is because flawed and manipulated input data and yet unknown climatic processes will not produce accurate results. Water is a very unique substance when compared to other substances. It is the only substance that exists in the form of a solid, liquid, or gas. Water can expand 1,600 times, making it a tremendous absorber of heat, and likewise can reverse that expansion as it gives off heat. Water has a heat of fusion of 144 BTUs per pound, one of the highest known for any substance. Water heat of vaporization is 980 BTUs per pound. That is why it absorbs so much heat to help modulate Earth atmospheric temperatures. If you live in a coastal area, you know what that means. Water expands when frozen nearly 10 times its unfrozen volume. Keep in mind that all substances that are dissolvable in water are captured in the frozen water, ice, snow, etc. Finally, water can be boiled to a temperature of 212 degrees Fahrenheit when it then can become steam. It can be further superheated to various temperatures up to 1,500 degrees Fahrenheit under various pressures. This graphic of changes in state of matter shows how energy increases particle motion, causing a change in state. Here is an example of the previous graphic. Nitrogen is the most abundant substance in Earth's atmosphere, making up over 77% of the atmosphere. This shows how nitrogen can be converted from its normal gaseous state to a liquid by decreasing temperature to minus 320 degrees Fahrenheit. Liquid nitrogen is used as a coolant, a cold storage method, and for medical uses. It has also been shown that substances can be changed directly from a solid to a gaseous state. This is called sublimation. Here you see one form of frozen water, icicles. Here the icicles are formed from melting snow that is then subjected to freezing air temperatures, or flash freezing. This picture shows a beautiful example of the three phases of water. You can see ice and snow, solids, water vapor, steam, and liquid water, all in one place. Snow is, of course, a very important phase of the water cycle because in many parts of the world it conserves water in its solid form for use later during warm periods when water is needed for human use. Because of differing weather conditions all around the world, many humans have always had to adapt to the environment where they live. Because mankind has improved their ability to adapt with fossil fuel technology providing heat and cooling, living in any climate is far more survivable than past times. Here is an example of the gaseous phase of water. Steam produced by geothermal wells beneath the Earth's surface. Many communities generate electricity from these sources, another great human innovation. Now for a deeper dive into the magnificent substance called water, let's look at some of the physical and chemical properties of liquid water. First, its density. It has a maximum density at 4 degrees centigrade, not at freezing point. This expands upon freezing, but properties are unusual. In lakes, it prevents freezing up and causes seasonal stratification. So now for the melting and boiling points, they're abnormally high, and that permits water to exist as a liquid at Earth's surface. Its heat capacity is the highest of any liquid except ammonia, and this moderates temperatures of Earth by preventing extremes. Water has one of the highest heat of vaporization of any substance known. This is important to heat transfer in atmosphere and oceans. It moderates temperature extremes. Water has a very high surface tension, which regulates drop formation in clouds and rain. Water has a high absorption of radiation. It's large in infrared and ultraviolet regions, but it's less in visible regions. This is important to control on biological activity like photosynthesis in water bodies and on atmospheric temperature. Water has great solvent properties for ionic salts and polar molecules because of its dipolar nature. This is important in transfer of dissolved substances in hydrological cycle and in biological system. Water has so many important effects on the climate of Earth that it is hard to determine which is the most important. The evaporation process is clearly one of the more important effects. It conforms to the thermodynamic theories developed by mankind for understanding temperatures in the atmosphere and for designing cooling and heating systems around the globe. Humans have invented many devices that use the evaporative processes to improve life on Earth. Heat of vaporization is the amount of heat required for 1 gram of a substance to be converted from a liquid to a gas. Hydrogen bombs make it difficult for water molecules to escape the liquid state and are responsible for water's high heat of vaporization. The hydrogen bonds must be broken before water can evaporate, and this requires considerable energy. Because water has a high heat of vaporization, it helps our bodies and our planet to maintain our temperature within a tolerable range. When we get hot and sweat, water evaporates from our skin and cools us. Since the evaporation of water requires a considerable amount of energy, it is very effective in cooling us. Water also helps moderate global climate by absorbing solar radiation and dissipating the heat by evaporation. Gases dissolve in water. This includes oxygen, not to be confused with the oxygen that is part of the water molecule. Dissolved oxygen can be easily extracted. Carbon dioxide also dissolves into water, a fact that explains why this gas has minimal effect on Earth's climate, especially since it is a minuscule part of the atmosphere. The greenhouse effect is a term that was coined by scientists to help explain their theory of how Earth temperatures are modulated. From a theoretical point, the term itself is incorrect because it implies that Earth gases are trapped within an enclosed greenhouse. Nothing is further from the facts, but the term serves to support the falsehood of global warming caused by humans. The greenhouse CO2 effect is a minor player in global warming. The important climate thermostats are too chaotic to model. For example, precipitation and cloud formation. A 2% precipitation change more than offsets a doubling of CO2, but rain and clouds are too chaotic to model, even short term. The Pacific heat vent, observed and powerful, but cannot be modeled. It is also a stable temperature control thermostat. Water vapor is the primary greenhouse gas, overwhelming CO2, but even the EPA will not call water a pollutant. The clouds and humidity factor is chaotic and bogglingly complex. High clouds tend to warm the planet, but at the same time, low clouds tend to cool it. Which effect rules? Nobody knows. Forgetting the incorrect greenhouse term that should more correctly be termed atmospheric conditioning phenomena, here is a look at atmospheric gases that are thought to have an impact on Earth temperatures. Remember that these are theories, not proven facts, because the sun cannot be overwhelmed by any Earth phenomena. So the greenhouse gases are said to be water vapor, CO2, methane, N2O, and other, and then the human-caused CO2, which is a very small part. Water vapor is Earth's most significant greenhouse gas, accounting for about 95% of the greenhouse effect. CO2 is only 3.6% of the greenhouse effect. The greenhouse effect is over 99% natural. Nature produces 99.72% of the greenhouse effect. Therefore, man contributes only 1/3 of 1%. Therefore, water vapor, which absorbs and traps heat from the sun, is the most dominant factor over the temperature of our atmosphere. Just look at the facts about CO2. CO2 in the atmosphere is 720 billion tons. The human output of carbon dioxide is 6 million tons, a tremendous difference. So how could humans be causing the Earth to warm? Not possible. As explained earlier, water can exist as a solid, liquid, or gas. This graphic shows the phases and the pressures and temperatures necessary to cause a change of state. Water has a solid, liquid, vapor triple point. From that point, liquid, vapor, and solid is determined by temperatures and pressures as shown on the chart. This graphic is even better. It shows the pressure and temperature effects on the water molecule that causes the change of state. In the upper right-hand corner is yet another phase called the supercritical fluid. This is the phase known as superheated steam. It causes the molecules to collide and otherwise behave in motions not common in other phases. Because of this motion, it contains great amounts of energy. You can notice how the molecules are separated or close together depending on what phase the water is in. The supercritical state is an additional phase to water's more familiar solid, liquid, and gaseous phases. Under these conditions, the physical properties of water change, as shown here, from water to a transition state, to making steam, and then superheating that steam to the supercritical state, shown on the right lower corner. This graphic shows a few of the molecules within Earth's orbital sphere. However, when it comes to the complexity of the interaction of various molecules in the atmosphere, it is clear that there is more for mankind to figure out. Science is never settled. We are focusing here on water and carbon dioxide, but other molecules come into play. Here is but a small example of the physics involved when trying to analyze how different atmospheric substances affect the weather and climate. This shows the differences between two very common molecules, water and methane. Water has what is called a polar bond, and methane has a non-polar bond. A polar bond means that there will be strong interactions between polar molecules. Methane does not have a polar bond, so there is weak interaction between molecules. How a computer program contains code for these interactions is a mystery. Think of all the molecules in the atmosphere with different properties, different volumes, etc., etc. Then you begin to get the picture. It is very chaotic. Photosynthesis. Thank God for this process that gives Earth life. It requires the sun, carbon dioxide, and water to give us oxygen and green plants, all helping to sustain life on Earth. Here shows the human-derived equation for the photosynthesis process. Everything depends on the sun. Too bad politicians can't convince us it can be controlled by humans. This graph depicts yet another of water's important characteristics: change in density with change in temperature and change in pressure. This characteristic is a key driver of the troposphere climate and affects temperature, cloud formation, and many other factors. This graphic illustrates those effects of temperature and pressure on the troposphere with respect to air density. Because of gravity, air molecules are less and less dense with increases of altitude. This graphic consolidates much important information. Many people forget that nearly all weather on Earth happens within 6 miles of sea level. The red line on this chart shows the standard temperature lapse rate as you ascend into space through the troposphere, tropopause, stratosphere, etc. This temperature lapse rate has been documented by temperature variations exist everywhere in the Earth's troposphere regardless of the amount of CO2 contained in that air. This is called weather, and it drives meteorologists crazy trying to forecast hourly, daily, and longer-term conditions. They do not use CO2 to predict any weather condition, but moisture in the form of water vapor, humidity, is always considered a telling factor about the phony CO2 hypothesis. This slide illustrates how the density of gases varies depending upon the gas molecular weight. Density varies with the type of molecule. With the number of molecules constant, the density varies with the molecular weight. The higher the molecular weight, the higher the density. Here is an illustration of how the density of gases changes with their temperature. As molecules warm, they become less dense and they rise in the troposphere. This pictorial illustration of molecules in the troposphere is helpful in understanding the complexity of water. Fewer molecules means calmer air. Temperature of the atmosphere correlates with the sun, not human hydrocarbon use. Our Earth's atmosphere, a lot is known, a lot is unknown, a lot is under dispute. The past 250 years have been watershed years for human life. Knowledge of the universe and our own planet has helped mankind to improve life and adapt to weather conditions that were life-threatening in prior years. The next few graphics depict just a few of the complex phenomena of the universe and Earth atmospheric science that needs further study and illustrates why science is not yet a reliable tool for making public policy. Before we take a deeper look at the atmosphere of Earth, it is helpful to consider the big picture. Earth is but one of many planets within the solar system. Mankind has not fully comprehended solar effects from unknown factors, and even if it was known, what could be done? Science has helped to develop various theories about the universe, but mankind has not concocted ways to test the theory. Suffice to say, we just do not know. We do know, however, that the sun has always impacted how planet Earth behaves. For centuries, Earth was not inhabited by humans, and then for centuries after humans inhabited the Earth, they were at the total mercy of weather conditions for their very survival. Depending on whom you believe, it took mankind 50,000 years to develop the capacity for language. It has been a long struggle since then to get to our current social human condition. We must not allow a few misguided humans to reverse progress as a result of unknown science. One aspect of the Earth's atmosphere that is a challenge for those attempting to quantify atmospheric conditions at any point in time on Earth is the planet's rotational effect. Earth's orbit around the sun is not circular, nor is the Earth rotation axis fixed. Like anything else, it cannot be controlled, so the effects from it are not controllable. Computer program input will always be affected by unknown atmospheric phenomena caused by variable conditions like these. Furthermore, to quantify a weather condition at any time in history is meaningless data without knowing every piece of information about all pertinent conditions at that location and at that point in time. Now, for a very short and very simplified explanation of a very complex subject. Earth receives all of the life-sustaining energy from the sun's solar radiation. The atmosphere prevents the planet from becoming just another lifeless globe. Incoming solar radiation from the sun is variable and dependent on factors that are not fully understood. The sun seems to experience variations in cycles similar to the other planetary bodies that make up the universe. It is interesting that most of the sun's radiation is blocked by Earth's atmosphere. This helps explain why Earth, unlike other planets in the universe, supports life. Of course, water, oxygen, and CO2 helps. This graphic shows the scientific attempt to quantify the global atmospheric energy, both incoming and outgoing, assuming it will always seek a balance. Keep in mind that these values are all assumed and cannot be accurately verified. Once numbers like this are used in determining weather and climate science, it is immediately only theoretical, not real or settled science. This graphic illustrates only a few of the complex attributes affecting weather and climate. Now just imagine the complexity of manipulating variable data like this at locations all over the globe and then producing a meaningful average of Earth weather and climate. The jet stream is yet another part of the overall Earth climate system that escapes scientific ability to predict its behavior. How to model this effect in a computer is beyond me. Have a look at this video depiction of the jet stream and you begin to get the picture. This changes almost on an hourly basis in a big way and has a huge effect on weather around the globe. This graphic summarizes the gases in Earth's troposphere. Nitrogen and oxygen dominate the gaseous compounds. These are the gaseous compounds that scientists say make up the greenhouse. As said before, these gases should be titled atmospheric conditioning gases rather than greenhouse gases. None of these gases are trapped in a greenhouse. Also, notice how water vapor is the dominant gas. This graphic is appropriately titled Gaseous Composition of the Troposphere. Composition of all gases varies all around the globe, and each gas seeks its own level based upon physical properties, wind conditions, temperature conditions, etc., etc. As you can see, oxygen and nitrogen are the largest components of the atmosphere, and water vapor is more than carbon dioxide by orders of magnitude. This graphic gives the composition of the main gases in the lower atmosphere in percent by volume, concentration in part per million, average residence time, and variability over time and spatial scales. It is not realistic that the composition of these gases would be the same all over the globe. Scientists attempt to average gaseous compositions but this is impossible with anything close to accuracy. Weather is so chaotic that every location would display differing concentrations because of its location on the globe, its local weather conditions, the local altitude anomalies, and the local terrain impacts, and on and on and on. The chart is useful for promoting the false premise that a greenhouse effect makes carbon dioxide a dangerous and polluting substance, when just the opposite is true. But this even fails when you compare the volume of water with that of carbon dioxide. Water is 4% of atmospheric gases, and carbon dioxide is 0.0397% of the atmosphere. Therefore, water is 100 times more abundant in the troposphere than carbon dioxide. When you look at how oxygen is produced, one thing is abundantly clear. Water is involved in nearly every process. Here you see that even some of the oxygen is made in the atmosphere where sunlight breaks down water. Carbon dioxide has been a part of Earth's atmosphere for billions of years and has been proven to be orders of magnitude more abundant long before humans occupied the planet. Beginning in the early 1900s, mankind is accused of increasing CO2 levels to dangerous levels through the utilization of fossil fuels. CO2 levels over this period increased from a dangerously low level of 180 parts per million to a level of approximately 410 parts per million. Without levels of CO2 greater than 150 parts per million, Earth would be devoid of the plant life essential for producing oxygen, yet demands continue to lower CO2. Higher levels of CO2 are beneficial for all life on Earth. Carbon is the main constituent of all living organisms. It is an integral part of all the major organic compounds of the protoplasm, like carbohydrates, fats, proteins, and nucleic acid. The sources of carbon are carbon dioxide in the air, carbon dioxide or carbonic acid or bicarbonates, all in water, coal, petroleum, natural gas in fossil fuels, carbonates and graphite in rocks, limestone in the oceans. Carbon dioxide returns to the biosphere in 5 ways: by plants and animals during respiration, by decomposition of organic wastes and dead bodies, by burning fossil fuels, by volcanic eruptions, and by weathering of rocks. This graphic illustrates the fact that CO2 is soluble with water. The combination produces carbonic acid. Carbon dioxide is needed by plants when they make food during photosynthesis. All living organisms breathe out carbon dioxide when they make energy from food. Carbon dioxide is a normal component of all natural waters. Its sources are atmospheric diffusion, respiration of species, biological oxidation of organic compounds. CO2 is not particularly toxic to fish if a sufficient dissolved oxygen is available in the waters. Maximum tolerance level of fish is about 50 milligrams per liter. This illustration shows in graphical form that atmospheric carbon dioxide gas content is so small it is invisible on a bar chart. The lower chart shows that human-caused CO2 emissions contribute only 0.117% to the total greenhouse effect. This graphic puts atmospheric carbon dioxide in perspective. On the left axis, CO2 is listed in values from 0 up to 0.5% of the total atmospheric gases. The bottom axis shows years from 0, the birth of Christ, until year 2000 AD. First, look at the red line on the chart. It represents the percent of carbon dioxide in Earth's troposphere since approximately 500 AD up to 2000 AD, based upon information obtained by scientists from the ice cores in the Earth poles. As shown, the CO2 values have rarely been lower than current values of 0.038% and have at times been as high as 0.05%, a value that is preferred for a healthy environment. Second, look at the value of 0.1%, that is the CO2 percent inside an average house. It is unlikely atmospheric CO2 will ever reach this value. Third, look at normal human CO2 limits as defined by OSHA. It is 13 times the present atmosphere conditions. Finally, note that water vapor is 100 times current CO2 values, making it clearly the modulator of atmospheric temperature and weather conditions. Now let's be clear, CO2 is not a pollutant. It is critical for life. A doubling of CO2 would greatly improve crop yields and forest growth. Decreasing CO2 to half the current percent would be catastrophic. Plants would begin to die, causing humans to starve and so forth. So here's a claim that I make. About 500 million people, 7% of today's population, are alive today who wouldn't be if carbon dioxide had not risen in the last century. Here is a graphic produced by the EPA that verifies everything claimed in this video. It shows that aggregate emissions from the so-called 6 common air pollutants was down 73% since 1970. It also shows that CO2 emissions is up by 23% since 1970, and energy consumption is up by 44%, while population increased by 59%. Meanwhile, agriculture production increased dramatically because of the increase in CO2. All of this while gross domestic product was up a staggering 262%. These factors point to a need for more of the same, not putting the brakes on the energy industry and the utilization of fossil fuels. This graphic explains the difference between physical and chemical change. It is very important because physical change, such as that experienced by water, is temporary. No new substance is formed, and change can be reversed. Chemical change, on the other hand, is permanent and cannot be reversed with simple methods. Energy is released or absorbed. Combustion is an example of chemical change, and world chemists have developed a multitude of products using chemistry. A world-class example of chemistry is the photosynthesis process that converts CO2, sun rays, and H2O into oxygen and plant life. Thankfully, this change is not temporary, nor can it be reversed. Now for a focus on water vapor, clouds, and carbon dioxide. The global warming theory that blames human-made CO2 for atmospheric warming has been disputed from the beginning. This is because UN scientists failed to accurately take into account water vapor in the troposphere. This, of course, skewed results and forced a much higher troposphere temperature. Somehow, this bogus data was convincing enough for world politicians and courts to define CO2 as a pollutant. Now let's take a look at the real world. This graphic is very important because it shows how water takes energy from the environment and how energy is released back to the environment. This is the key in developing clouds and other weather phenomena that is important to mankind's existence. This graphic illustrates the huge effect that the sun and oceans have on the development of water vapor and clouds in Earth's atmosphere. And CO2 simply does not have adequate volumes and the ability to absorb and release enough energy to affect the atmosphere, especially the minuscule amount of human-made CO2. A very simplified graphic of the climatic effects of the oceans. Waters of the oceans are not only a huge reservoir for absorption of the sun's radiation, but the oceans also act as one of the mechanisms for cloud making through the evaporative process. Carbon dioxide is absorbed into the oceans and released back into the troposphere as temperatures rise and fall. Another graphic illustration that shows how clouds are formed over land mass. This process also is a factor in the development of air movement, wind generation in the troposphere. How clouds form is very, very complex, and as far as I know, is not something that has been able to be modeled by a computer. However, these clouds have a tremendous effect on global temperatures, dwarfing any CO2 effect. Here is a look at the National Weather Service chart for identifying different forms of clouds and their characteristics. It illustrates how complex and difficult it would be to handle all of this in a weather model. And as far as I know, it has never been accurately done. Clouds in the troposphere are unique all over the world. This illustrates the tremendous heights they can reach into the atmosphere in certain parts of the world, and also shows how very, very difficult it would be to model these clouds in anything relating to accuracy. These photos were snapped from my deck on a typical fall morning in California. Just over the hill to the right is the ocean that frequently has a marine layer along the shores during all of the seasons. Each photo was taken about 5 minutes apart. You can see how quickly weather patterns change. Warm inland air brings the marine layer through the hillside gap, where it goes through the fog phase, then evaporates into water vapor. A beautiful, complex event that is interesting to watch. Notice also the clouds at higher altitudes and the contrails from jet airliners that show the effects of temperature and winds aloft. Imagine trying to model these conditions and averaging them with changing conditions minutes and hours later. The city of San Francisco, where the morning fog may chill the air, a beautiful weather example. This slide is appropriate to show after the morning fog in San Francisco, the changes that are made to the fog into water vapor through the sun's radiation, the conduction and convection processes, shows that carbon dioxide has absolutely no impact on any of these processes and cannot materially participate in any climate conditioning, such as warming or cooling, because of the extremely low volumes of CO2 in the atmosphere. Cloud formation is indeed complex. It relies on the sun's radiation, conduction from the ground, which heats the air, and then the air rises and convection takes place. So without all these complex processes, clouds would not be formed. And it's clearly very difficult to model this all over the Earth. This graph illustrates yet another complication, and it is the effect of the dew point temperature in the formation of clouds in the troposphere. The dew point is the temperature that air must be cooled to achieve a relative humidity of 100%. At this point, the air cannot hold more water in the gaseous form, and therefore clouds will form. It is informative to know how most of the world weather and climate data is obtained, and how this has been performed in the past as well as in the present. Without weather history, it is impossible to judge or even think about future weather and future climate. Recorded weather data is obtained with radiosonde instruments and balloons that were released into the atmosphere. As technology has advanced, many other parameters were added, and digital measurement and recording replaced analog instruments. Weather balloons operate up to altitudes of 25,000 feet before they burst. While they do not provide direct forecast information, they do help explain why there are different types of weather at various locations and altitudes. From a historical perspective, the data is extremely valuable. Unfortunately, climate models still cannot accurately hindcast weather to match conditions proven by the past data. This visual gives you an idea how many weather stations there are around the globe. All are not radiosonde, but you get the picture. When the data is retrieved from the radiosonde device, it is decoded and plotted. This is a typical example of one of the plots. Meteorologists prepare temperature and dew point charts called skew-t plots to illustrate information they have gathered from the radiosondes. These represent the dew point, which is calculated from the relative humidity, and air temperature, shown in red on the right line. This shows an excellent example of how skew-t plots can be compared from station to station so that weather patterns may be established for a region. Aviation weather has been improved significantly and provides safe flights to anywhere on Earth that has continental airports. Accurate information for more than a 24-hour forecast is not possible, but aircraft pilots provide continuous real-time updates that help provide for really good accuracy. This shows an example of how valuable it is to know weather conditions at various altitudes. This helps meteorologists analyze, and predict developing weather patterns. Now consider what all of this means to weather and climate. Weather phenomena are complex indeed. Weather systems like this heat wave form when high pressure aloft from 10,000 to 25,000 feet strengthens and remains over an area for several days or weeks. This is common in summer in both the northern and southern hemispheres. Many of the weather systems aloft are the result of the jet stream. It is common knowledge that warm air rises. It is normally assumed that this is because warm air is lighter than cooler air. While that is true, there is a more fundamental process that takes place for the cause of rising warm air. Warm air rises primarily due to its lower density, but even air of any density will not move or rise by itself. Isaac Newton's first law of physics is that the velocity of an object will remain constant unless another force is exerted on that object. This is why decreasing the density of air alone is not sufficient enough to cause air to rise. The force is gravity, as shown in this graphic. This explains why many weather systems form along fronts, like thunderstorms. It also helps to clear up a fundamental question as to why such minute amounts of carbon dioxide in the troposphere find their way to ground level so they may help propagate the photosynthesis process and create the oxygen for life. This is because the CO2 molecules have a molecular weight of 44.01 and a specific gravity of 1.522, while air-specific gravity is 1. Gravity will keep the more of the carbon dioxide molecules near Earth's surface than water vapor molecules. It has been shown that subvisible cirrus clouds are corrupting information obtained from satellites. Clouds, aerosols, and subvisible cirrus high-altitude clouds prevent measurement of the entire atmospheric column. An analysis of available global data suggests that a space-based instrument will see cloud-free scenes only about 10% of the time. This graphic is verification that CO2 is not the culprit for weather-related death rates. It also articulates that deaths caused by natural weather disasters and other disasters have been reduced dramatically since mankind began to utilize the energy from fossil fuels to protect humans from extreme weather events. The introduction to this video contained the statement, "Mankind does not and never will have the ability to change or control climate." Yet here you see so-called supercomputers that are used to produce weather forecasts and climate forecasts. The motion of air in the atmosphere is very complicated, and even if you could simulate every motion, it would be impossible to predict the motions seconds or minutes later, let alone years or decades later. So meteorologists predict a 1 to 7 day weather period because with 50% accuracy, people think they can get by. Things are different when you talk about climate, which is basically 30 years worth of weather. We must reject the carbon dioxide theory that claims that Earth is doomed and stop all of this political theater. It is not acceptable to eliminate the use of fossil fuels based upon a flawed CO2 theory. We must all realize that we live on a planet where water modulates climate. Carbon dioxide propagates plant growth through the photosynthesis process, and more is needed, not less. It is rare that water is the focus of any climate change discussions, so I hope you found this video to be informative and useful. I barely touched on the history aspects of the atmosphere and the importance of water to humans because the subject matter is endless. One of the things that I've found out over my lifetime in the engineering profession is the fact that weather and climate are not to be taken lightly. They are far too variable to be predictable, and I couldn't change them even with prayers. For the last 50 years, it has been my absolute pleasure to participate in the development of projects that have improved life for literally millions of humans. All of these projects involve energy in one form or another. I was fascinated by the mathematics and sciences that helped me set parameters for designing power systems, chemical plants, refining systems, and many other processes. Likewise, I was fortunate to work in the key industries that made the changing improvements in the world, like oil production, oil refining, electricity production from all of the fossil fuels, coal, natural gas, oil, propane, and even methane from human waste. I have conducted mathematical calculations for the combustion of nearly every fuel known to mankind. Another facet of my engineering career was related to the betterment of the environment. Long before the EPA was created, engineers began to work on methods for reducing air pollutants and water pollutants. These efforts were instrumental in reducing emissions far below the levels that cause human health impacts. When it comes to the effects of carbon dioxide on the environment and the climate, history has shown with absolute clarity that more carbon dioxide is better for mankind. All of this nonsense that carbon dioxide is a pollutant to be controlled by humans is nothing more than political theater and make-believe science. Humans cannot survive on a carbon-free planet. For those that believe otherwise, perhaps they need to visit the moon or other water and carbon-free planets and find out for themselves. Thank you for watching.